Hello, everyone. My name is Shankar. I work at Meta, and I'm going to be talking about accelerating GenAI deployment at scale with media understanding and evaluation with my teammates, Nick, Ryan, and Chi. Okay, first a little bit. 4 speakers for a 15-minute talk seems a bit excessive. But a little context is like, we realized that all of us are working on sort of work streams which actually were related. So the connections between them evolved sort of organically, and we thought that a joint talk with all learnings would sort of make more sense. First, I want to talk about the challenges of video GenAI deployment. So that's really what I'm going to be focusing on talking about. And primarily, what we have been doing, our team has been doing, is working on enabling development, improvement, and iteration of GenAI models for the Meta ecosystem. And in particular, some of the recent use cases include lip-synchronized voice translation.
De coco, banana y dulce de leche. Esta receta fue una de las primeras que subí a las redes. Hace poquito la volví a descubrir y le hice un par de modificaciones para que sea aún más deliciosa.
With coconut, banana, and dulce de leche. This recipe was one of the first ones I uploaded to social media. A little while ago, I rediscovered it and made a couple of modifications to make it even more delicious.
Mi lengua materna es el español, pero fíjate, ahora también puedo hablar inglés a través del doblaje automático de IA. Mis labios se sincronizan con la traducción y todo. Es increíble. Qué cool poder conectar con personas y audiencias que hablen inglés.
My native language is Spanish, but check it out, now I can also speak English through AI automatic dubbing. My lips are synchronized with the translation and everything. It's amazing how cool to be able to connect with people and audiences who speak English.
And more recently, we have been working on Movie Gen. And you might have seen from Jordi's presentation about video restyling. So what we see is the common set of challenges across all these different use cases is twofold. One is, how do we ensure having consistently reliable and delightful experiences for all user-generated content? And the second aspect is, how do we enable rapid and safe improvements through iteration of models? These are the two main challenges that we see. Okay, now diving a little bit into these two challenges and why they arise. The first aspect comes from the diversity of user-generated content. So user-generated content is like often very different from dataset that's used for both developing and improving GenAI models. So some of the common problems that we see is, like, for example, on the video side, you see that there is like different shots, there is like black borders. On the audio side, we see presence of echo and noise. We also see audio-video quality, which is far from pristine. Now, these problems end up showing up as inconsistent output quality of the GenAI models in practice. The other main problem that we face is the lack of reliable metrics that could track user-perceived quality, which could help with both guiding model development as well as for a safe rollout of the models. And so to solve these problems, we have like two main categories of investment. The first one is we have been investing in media understanding algorithms, which basically the examples of such includes like detecting shot change, boundaries, whether a video is a slideshow or not, as well as detecting presence of noise. In addition to that, we also have quality assessment metrics for the source audio and video quality. Why do we do this? This allows us to determine whether a particular content is suited for a particular GenAI model use case, as well as optimizing the application of the GenAI model for that specific content. And we're going to be talking a little bit more about it in detail next. The other main category of investment is subjective, objective evaluation frameworks. And here, particularly, we are invested in making subjective evaluation easy to use, cheaper, and faster. And again, this is to accelerate model development. And the other aspect here is to use subjective evaluation to both validate and improve objective metrics. So the structure of the talk is going to be, next, Nick is going to be talking about some of the media understanding algorithms. And then Ryan is going to be talking about quality evaluation for one specific use case. And then Chi is going to talk about how bringing it all together for the use case and show how this all works. And again, we're going to be diving into a specific use case, but these broad lessons apply across use cases. Thank you.
Hey, hi everyone. So my name is Nick, and I will be talking about the video understanding for optimizing GenAI training. And a little bit about myself, I work at Meta for designing the video encoding recipe for our VA, and then to trade off between quality and our compute at the meta scale. So this is what we bring to how do we optimize this. So as Shankar mentioned earlier, right, this is one of the biggest challenges, the variety of content that we're dealing with, and both for training as well as product use cases. So here we are using a low-level but efficient video understanding signals to help with optimize for the training. And here I'm only going to show you some high-level example, and then pick 3 example here, which is shot, motion, and border, to kind of demonstrate what this means, but what I mean by using a low-level efficient video understanding signals. So this is the first one. This is, I think people here probably understand this very well. It's like normally video consisted of multiple shots, right? And then this is just like an example of like a short video with a few shots, about 10 shots in this video. And if you work on a particular model and try to train on it or use the model on a particular video, it is crucial that you want to know where the shot boundary is so that you don't apply the model either across the boundary or introduce some artifacts, right? So this is really the crucial first step as the normalizing first step so that you don't introduce anything downstream. And then either you can segment the video into shots or you can basically supply this as the metadata for any downstream to process. And then now this is the next example. So another example where we work on video, so we know this is how important this is. So by doing something very efficient, like in this example, we're doing a block-based motion vector field that you can get a lot of information, like the screenshot on the left, it's showing a panning camera motion. And on the right, you can clearly see a couple objects moving and the thing is static. So these information will help feed into the downstream pipeline for training as well for inference. Some other thing you can infer from this is, for example, is this thing shaky, which you see a lot with a lot of user-generated contents. And last example I'm giving is border detection. This is like a very old problem, right? Like, for example, in the old day where you have a movie show on TV, you have a black letterbox. So cropping it out is a very common thing that we do in various different things. But with user-generated content, we're seeing this kind of stuff. And then this is just one example, there are more. So there are border, but then they are with varying degree of context, right? In this case, it's a gradient color kind of thing. It could be some kind of blurred effect behind. It can have some text at the border part. There are all kinds of stuff here. But the important part here is we need to do this kind of stuff so that we can either attach this as a metadata downstream or you crop it out. So these will be crucial to help with the end-to-end pipeline for both model training and inference. And next, I'm going to hand it over to my colleague, Ryan.
Hello, everyone. My name is Ryan Lei. I'm currently also working at the Meta Media Foundation team as a codec specialist. Actually, in the past few halves, I spent a lot of time working on actually pre-processing and enhancement. So today I'm going to talk about one of the recent technology we enabled for the movie gen and the restyle project that Jody mentioned, which is a super resolution. So as Jody showed in his talk, he gave a lot of very details about the movie gen pipeline and the restyle project. So for here, I just provide a very simplified processing flow. as Jody mentioned, when we have a user input video, so by leveraging the movie gen model, we can change its style. And after that, based on what the creator wants, we can actually increase the video resolution, quality, and adding other invisible watermarkings or overlays, going through this post-processing pipeline and generate the final video that user want. So this is kind of just one example of the video we are seeing from the movie gen model and the Restyle project. So here specifically, I want to talk about the super resolution solutions we added in this post-processing pipeline. So we basically enable the machine learning-based super resolution technologies. It gives us much better quality than conventional upscaling algorithm. I hope you can see it from this, side-by-side comparison. So when enable super resolution at scale, we are facing a lot of challenges, as my colleagues has already hinted. So first of all, as you may know, there's many super resolution algorithms out there. So every year, maybe a few hundred new algorithms will come up. So for us, the challenge is we need to benchmark and evaluate, based on the quality and complexity, and see which one is the most optimal solution we can use. Second is, as also previous colleague mentioned, right now it's different from the video compression domain. We have well-established quality metrics and methodologies to benchmark different codecs encoders. But for super resolution, and especially other video enhancement based on machine learning or GenAI models, there's no reliable metrics or methodology we can use to validate how much quality improvement we can see from different solution algorithms. So on the other hand, also there's no kind of reliable metrics can help us detect if certain algorithm can introduce some artifacts, such as in the super resolution case, it's very common to see over sharpening, over smoothing, or sometimes you can also see the color differences, as I showed in this slide. So in order to address these challenges, we have to take a very practical approach. So we leverage large-scale subjective evaluation to help us understand and answer a few questions. First of all, among all different super resolution algorithms we want to benchmark, which one gave us better quality that viewers are more preferable. Second is, at the time when we do subject rating, we also calculate different objective quality metrics. We want to understand which objective quality metrics correlate better with subject rating. Then we can use that, deploy it at the scale. The last one is also based on subjective rating. We also want to see what algorithm or what solution will likely to introduce some kind of artifacts, or for some type of video or some use cases, whether the super resolution can actually improve quality or not. So we like to know all those possible issues, then we can better filter them out in actually production use case. Also, we work very closely with academia and other companies. We see this is a common problem, like any company want to deal with GenAI content, they will face similar challenges. So we work very closely with universities and standard bodies to trying to encourage the researchers to develop more reliable quality metrics and methodologies for this type of challenges. So next, I'm going to hand over to my colleague Qi to talk about some learnings we got from the subject evaluation.
Hi, everyone. I'm Qi from Meta. I'm a software engineer working mostly on the media quality assessment, as well as the VOD and the live streaming quality and latency optimization. So in this section, we will talk about how to address the quality challenges mentioned previously. And our solution is we will use integrating the subjective and objective evaluation, as well as applying media understanding. So we will first talk about how we are assessing the media quality and the model quality with the subject evaluation. And then we will talk about how to verify the effectiveness of objective metrics. And finally, we'll talk about how we are able to leverage media understanding to optimize the GenAI model deployment based on the content. The first, we'll talk about subject evaluation. And subject evaluation remains one of the most reliable way for quality assessment. And this is especially valuable and important for GenAI because sometimes the objective metrics correspondingly is not very reliable. So I want to mention that for the following slides, we will mostly use super resolution as a use case, as a continuation of a previous section. But the idea and methodology is broadly applicable and is generic. So here we will demonstrate a side-by-side video comparison, which is a typical subject evaluation setup, where there are two versions of videos. They are usually generated from two model versions and from the same source. During the subject evaluation, a rater will be asked to assign a quality score in the scale of 1 to 5, the higher the better, to each of the video for quality assessment. Typically, about 10 to 20 raters are needed. And it's worth mentioning that in order to get meaningful results, it's very important to apply the statistical analysis on top of the raw ratings. This is due to the nature of human ratings. It is noisy and it's because of human's bias and the inconsistent behavior. So what we do is we use the state-of-the-art serial analysis to recover the models from the noisy ratings. And we also use the two-stage bootstrapping to further make the confidence interval tighter. And as an outcome, we are able to not only achieve static quality assessment score results, but also our budget in terms of the money and the time of the model iteration is optimized. So next, we'll talk about how to verify the object metrics using the subject evaluation. And in order to apply an objective metrics, it's very important to understand its effectiveness for meaningful results. So here, what we are interested in is how well an object metric can predict the ranking order of model quality. So here is how we do this. For super resolution, assume we have a set of 5 algorithms and one baseline. First, the ranking order can be measured by the subject evaluation, basically the relative models improvement against the baseline, so that we have the figure on the left. And separately, we can also predict the ranking order by using an objective metric. For example, on the on the red figure, we are using an open source metric called UVQ, which is a no reference video quality metric published by Google. By measuring the quality improvement with UVQ, we also have another version of ranking quality. And by comparing these two figures, we are able to see that the ranking order of model, the algorithms predicted align well with that of subject evaluation. Basically, you can see the version 5 is the best in both objective and subject evaluation, and followed by the version 4, 3, 2, 1. So this means UVQ is a very effective metric for the case of super resolution. And now, in the final slide, we'll talk about how we can combine the evaluation learnings with media understanding. This is important because we can leverage the media understanding to target the kind of content benefit most from like GenAI or enhancement algorithm to maximize the performance. What we showcased is that by optimizing the deployment of super resolution against like the source video characteristics, we're able to maximize the performance. And here the source video characteristic is interested is the source video quality. So here is how we do this. So first we break a set of videos based on the source quality into high source quality videos and low source video buckets. And within each of the bucket, we measure how the super resolution can improve the quality. And what we do is that for high source quality, we measure the 5 versions against the baseline. And we are able to see that there are more statistic improvements compared to the low source video quality buckets. And those more statistic improvements are indicated by the green bar. While on the right side, the more gray bar means that there's neutral, non-statistic results. So this tells us the high quality source videos are really the videos can benefit most from this super resolution enhancement. We need to deploy against that. And also, learning from our previous evaluation, we have a metadata or video understanding signals called UVQ that can reliably detect this source video quality. Okay, so as a summary of our talk, at Meta, we have a goal to deploy, accelerate the deployment of GenAI model and also ensure the high quality. And we have been facing challenges, for example, and the user-generated data is very diverse, and that results in the inconsistent output quality. Another challenge is there's usually lack of reliable objective metrics. And our solution is that we apply our video understanding to optimize the deployment of GenAI model based on the content. And our video understanding signals are well verified by using the joint subjective and objective evaluation. So that's all for this talk. And I would like our team to get on the stage. Not sure if there's enough time for Q&A. Thank you.